time to start the last talk of this morning. We're very happy to have Wei Li today from the Chinese Academy of Sciences, and she will tell us about BPS algebras and representations from colored crystals.
Okay, thank you very much. Thanks to the organizers for this nice conference and for the invitation. Does anybody know why?
Sorry about that.
It's better now?
Yep.
Okay, so this talk is based on these three papers with my collaborators, Masahito Yamazaki, who's sitting there, and Dima Galakov, who's actually in job market this year. Okay, so the main questions we want to ask is what is or is there any algebraic structure underlying the BPS sector of a 4D include 2 gauge theory? So the element of these algebras are BPS states in the BPS states, and the multiplication is the fusion of 2 BPS states into a third one. So this is analog of the chiral algebra of 2D into 2 subconformal theory, and it's some robust information of the theory, and they control as well as it controls many aspects of the theory, such as the counting and the wall crossing, etc. So let me review a bit of history. So this actually the story starts already in 1996 by Harvey Moore. So they considered the fusion of 2 BPS states. And so later in 2010, by Conchavi Soipman, they make the story much more complete. So we only consider this fusion. The algebra is the so-called cohomological Hall algebra, the CoHa. So if you consider fusion is also natural to include a decaying process. So at the algebraic level, that corresponds to you also include a co-product. So you start from 1 BPS state and see how it split into 2 different states. So that corresponds to take the Drinfeld double of this CoHa. So the structure is some alpha-Yangian algebra. So in some special cases, this alpha-Yangian algebra is the universal enveloping algebra of some W algebra. So we see that we have a different formulation of this algebra, but in any of this is only known actually only for a few cases. So in this talk, we're going to focus on this the basis of this alpha-Yangian algebra. Okay, so the system we're going to focus today is type 2A string in generic Torre-Calabi-Yau threefold. And the BPS states are given by this D-branes wrapping on holomorphic cycles of the Torre-Calabi-Yau. And so we want to ask, what is BPS algebra? And second, if you get it, what can we use it for? So let me just tell you the results first. So the BPS sector can be described by include 4 quiver quantum mechanics. So the information is a quiver and the superpotential. So it turns out the BPS states have a very nice description in terms of a 3-dimensional colored crystal. And so our strategy is that we fix the BPS based on some answers. We fix how the BPS algebra's action on this set of crystals. And once we got that, we can derive the algebra from the action. So in some sense, it's a bootstrap technique. So actually, once you go through this argument, the end result is actually quite simple. So the input is just this quiver and quantum mechanics, and the algebra is this quiver Yangian, which only depends on this Q and W. So if I tell you what is the Q and W, you can write down this the whole algebra is just in half a page. It's very simple. So the advantage is that you can have very explicit algebraic relations, and also this is the same procedure that applies to all Torre-Calabi-Yau threefold, and this also can be very easily generalized to the trigonometric and elliptic version. Okay, so once we get it, once we get the algebra, we can study the representations. So it turns out that all these representations also is you can very easily study in the same framework. So the representation is described by the subcrystals of the crystal that we used earlier, and at the level of the quiver, it corresponds to a different framing of the same quiver. And so these subcrystals will describe other chambers in the from the wall crossing. And also it includes the open BPS counting. And then also there are many more subcrystals that we don't yet know what the BPS counting problem they correspond to. Okay, so let me start by we're going to have 3 parts. So I'll first explain in detail how to describe these BPS crystals, and then the second part I'll explain the direction of the quiver Yang, and then explain the representation and also the generalization to trick and elliptic. So the system is a type of play string on a toric labial threefold. So this toric labial you can think of as T2 cross R fiber over R3, and this this PQ web tells you where the fiber degenerates. So this is the simplest case. This is C3, and the more complicated one, roughly there are 2 classes. So those has no compact fourth cycle, so that correspond to the diagram with no closed loops, and those with a compact fourth cycle, so it has a closed loops. So the half BPS sector we want to focus on is this D64, D2, D0 wrapping on the holomorphic cycles. So we have 1 D6. So to start with, we don't. I wouldn't add any D4. So later you can add D4 that will correspond to the truncation of the algebra. So the question is, what is the BPS algebra underlying this BPS sector? So first, let me try to describe this BPS sector. So this is described by Inc4 quiver quantum mechanics. So the information is a quiver and the superpotential. So the quiver, the node of the quiver each node corresponds to a gauge group, and each error corresponds to a bifundamental. And the superpotential is some collection of a monomial from this bifundamental. So starting from a toric labial, you can write down this Q and W pair from this brain tiling technique, for example, by Hanani et al. So what's going to be useful for us is that the information of the Q and W you can repackage into a periodic quiver. So this is you draw this quiver on a T2, and so you draw it in such way that so the faces, the arrow along any faces is along the same direction. So for each loop, for each phase in the fundamental domain, that will correspond to 1 term in your superpotential, and the sign is determined by the orientation of this the arrows along the loop. So this is the simple example, the C3, and so there's 1 node and 3 adjoint, and so you have see there are 2 terms and they correspond to these 2 phases in the fundamental domain. Right. So so it turns out for each deep bound state correspond to a invariant state in your quantum mechanics, and which has as I explain later, which has a very nice 3-dimensional colored crystal configuration. And this generating function of this crystal will reproduce your BPS partition function. And so if you start with this periodic quiver and you do a particular uplift, and then you can obtain the entire 3D crystal, and then on the other way, when you project this 3D crystal, you will reproduce your periodic quiver. Right, so okay, let me give you the one example using the simplest example, the C3 case. So this is the periodic quiver. So this is supposed to cover the entire plane, but I'll only draw this part. So first you choose one node as your origin. So so this is a periodic quiver. So the only choice is actually in the color. I mean, but this guy has only one color, so it doesn't matter where you choose. So I choose this one as my origin, and so each atom in the crystal correspond to a path from your origin. So the origin, so this origin correspond to the leading atom. So the crystal start from this atom, and then this path give you this second atom, and this path give you the third atom. And then you see that there are different paths that you can go to the same atom. For example, this one you can either go by this or this one. So there's a notion of the equivalence of the different paths. So this is a correspond to the F-term constraint of your quantum mechanics. So when you grow this crystal, there's one important rule is that if you want to add an atom, so the atom that has some arrow pointing to it has to be already present in your atom. So this is easy to see if you think of this as a plane partition. So for example, this would be allowed plane partition configuration, but this one wouldn't. You see, if you think of this plane partition, I mean, this one would it's not allowed. So from this rule, it means that if you want to add this atom, I see that it has three precursor atoms that have both arrows pointing to it, but only one of them is present. So that means you cannot add this unless you add both this atom, both this precursor to this one here. Then you can add this last one. Okay, so so because we're going to uplift this periodic quiver to have a 3D crystal, so this you have a notion of how deep you are in your crystal. So if you start from this origin, if you follow these arrows, at some point you complete a closed loop. You go back to your origin node on your periodic quiver. Then that means that you're going deeper in your crystal. So for example, this one is the first atom in your crystal, and this one, you think of this plane partition. This one is here. So that means that you go from here to here to here, and then you go back. So this one, when you project, you have the same position, same coordinate on your periodic quiver, but they correspond to different atom in the crystal because they have different depths. So this is all old story before. So for each, so I just explained that for C3, when you go the entire crystal is plane partition, so you can have all these plane partitions. So this is another two examples. For example, for this conifold, this is the periodic quiver, and then the final crystal is this two-colored pyramid. And this is this orbifold, and because it's orbifold, so you have the same shape, but the three different colors. So the new ingredients we want to add is that, so for later we want to derive this BPS algebra from the crystal, we actually need a finer information for these atoms. So what we do is that we're going to assign equivalent weight to each atoms. So for each field, there's a weight. So because this each atom corresponds to a path, so the natural definition is that for each the weight for each atom is just a sum over all the weight along this path. And then you see this equivalence of path. Or for this definition to be meaningful, we need a constraint for this weight. So along each closed loop, the weight. The sum of the weight for these arrows have to be 0. And for this projection, we'll project the 3D crystal down to 2D. So, so this projection, it will project the different atom for this with the same coordinate they will have the same weight with different paths. So so finally, the number of the equivariant parameters. So if you when you start with this you have the number of this parameters, number of errors, and then I already said that we want to impose a loop constraint, which corresponds to the global symmetry of the theory. So the number of this loop constraint is the number of the faces minus 1, and then we're also free to impose the vertex constraint, which is the number of the so the sum of the weight from the incoming errors is the same as the sum of the outgoing errors. So once you impose both constraints, you see that the number of the equivariant parameters is 2, which is precisely the 2 equivariant parameter for this for the Clavion. Right. So before I go on, I want to clarify some potential confusion about the terminology confusion. So in this crystal melting literature, we usually think of this, there's a big crystal, and then you remove some atoms from a corner. So this is the melting crystal state, which corresponds to the excited states. So the crystal configuration that I'm going to, when I say crystal, it's actually correspond to the complement of this bigger crystal. So this is the C3 example, and this is the pyramid example. So we're going to focus on this small finite set that sit at the tip of your pyramid. So each state corresponds to some particular combinations of deep range. Okay, so now is the second part. I'm going to explain how to derive this BPS algebras. So actually, for the simplest case for the C3, the answer is already known. It's this alpha Yang GL1. Actually played an important role in the proof of the AGT conjecture. So this might look complicated, but let me just walk you through this. So if you, for the moment, if you forget about the coproduct structure, this is just associative algebra with the 3 families of generators here. And this psi is the Catan, and this E is the raising operator, and the F is the lowering operator. And in this definition, there's one. So remember earlier, for the C3, there's 3 errors and there's a loop constraint. So there are 2 equivariant parameters. So they enter in the definition of this manifestly permutation invariant rational function here. And so this is the quadratic part of the relation, and also there's also QB relation here. So if you're not familiar with this algebra, you might help to know that this is equivalent to a universal evaluating algebra of W1 plus infinity. So that's how they use this in the proof of the AGT. So the BPS crystal, they are just the set of all possible plane partitions, and the generating function is just this maximum form function. So this algebra has a very elegant action on this set of plane partitions. So this is actually rather important slide. So let me explain this in detail. So the important feature is that each plane partition is a eigenstate of this entire family of Catan, and it's actually very easy to write down the eigenvalue. So so vacuum contribute a factor, and then each atom or each box in your plane partition contribute a factor, which is this Wi-Fi factor that we see earlier, and then it's shifted by the equivariant weight of this atom. And so the raising operator, you start with the plane partition. The raising operator add 1 box in all possible places, and the F generator remove 1 box. And the position is given by the pole. So where you can add and where you can remove is given by the pole of this eigenvalue function. So so if you check, you can see that if you start from the vacuum, you apply E generator repeatedly, you can generate all possible plane partitions. Or conversely, you start from any plane partition and you apply F repeatedly, you can bring it back to the vacuum. And then all the poles of this chart function has a meaning. It actually corresponds to the place where you can add, where you place where you can remove. So that means that this the poles of this file can have to be near the surface of this plane partition. So also when you do this, the melting rule we mentioned earlier also is actually automatically satisfied. So so for this to happen, it's important that we have this. So this phi is this has this form, and also we need to use this loop constraint repeatedly. So for the general case, what are we going to do? So we see that this E phi F, this triplet, that's for just for the one node. So for the general Troy club YAO, we have many different colors. So for each vertex in your quiver, we'll have one triplet. So for each color is have its own Cartan and racing and long operator. And then for the to fix the relation, so our strategy is that we try to first imitate this slice to fix the action of this algebra that we don't know yet on the set of the color crystal that we constructed earlier. So this is the ansatz here. So we just imitate how the alpha energy L1 acts on the plane partition. So now for each color crystal configuration is the eigenstate of all the Cartans for all colors. So and the charge function is it has a similar form. So vacuum contribute a factor. And so now the point is that so this is the charge function for color A. So all the atom, irrespective of what color is, it will contribute to this. So the atom of color B will contribute this factor. So there will be a relative binding factor. And then the racing operator only take care of the adding of the color A atom, and then F of A only remove the atom color A. And then the where you can add and where you can remove is also again controlled by this charge function color A. And then what we want is exactly what happened for the alpha energy one. We want that if you apply E, you can generate the entire crystal, and when you apply F, you can reduce it to the vacuum. And then we want all the poles to have a meaning. It's either it's correspond to place you can add or a place you can remove. And so that means that when you grow this crystal, all the poles get pushed near the surface. So this is the ansatz. The only thing we haven't fixed is this bonding factor. So so
can I ask a question?
Yeah, please.
Are they near the surface or really at the surface?
I mean this. So you have think of the plane partition. You have a box there. So when you want to remove the box, that the pole is actually added the box. When you want to add, say you have 3 neighbors. So you have 3. So I mean, it's outside the boundary, but close to the.
Okay, that's what you mean.
Yeah.
Okay, thanks.
Yeah. So this is the ansatz. We haven't fixed this bonding factor. So actually the only thing, once we write down this ansatz, the only thing to fix is this bonding factor. So we fix it in such a way that this 3 criteria is satisfied. It's actually very, very easy to guess what it is. So what fits the bill is that for each the bonding factor from B to A. So for each arrow B to A, we get a factor in the denominator. And for each arrow from A back to B, we get a factor in the numerator. And we also need this loop constraint. How much time? I have 20 minutes.
You have 15.
So okay. So let me just explain a little bit of. So this is one example. This is an orbifold of C2 called C. So this is almost the simplest next simplest case you can consider. So this is the periodic quiver. And so the crystal has exactly the same shape as the plane partition, but now it has two different colors. So the color, when you go along two directions, where you do the orbifold, it will alternate. And when you go along the third direction, it wouldn't change. So let me just show you roughly how it goes. So it starts from the vacuum. So the vacuum will contribute to the chart function. But so we choose the crystal will start from color A, sorry, color 1. So it contribute to the chart function, the 1. And so then there's a pole. So this blue, the pole for the blue pole correspond to the place where you can add the first atom, which is blue. And there's no pole for the red one, so you can't add any red atom. And there's no, so now you use up all the poles, so you from the atom you can't remove anything. So and then so this is the initial state, and you this will contribute to, from this binding factor will contribute both to the color chart function color 1 and color 2. So and then you read off this poles and you see where you can add or remove. Okay, so so this is the initial state with this 2 atom. Now this is the first non-trivial case where you see a cancellation. So you see that having this atom, after you add this atom, you cannot remove this its precursor anymore. So that means it's implemented by this cancellation of this one. It cancels the original removing pole. So and then you see that there has 3 adding poles here. And so the melting rule is also automatically implemented. So suppose I want to add this 2. You see that there's no poles for you to add this 2. But instead, if I add another atom here, then this atom will give you some additional pole here. So one of them is the pole that you can use to add this this atom. Yeah, so this is the summary of the essential feature for this to work. So we see that each atom B will contribute a binding factor to the chart function color A, and then this is the equivalent weight for each atom, and the important thing is this binding factor here. So this will make sure that the poles always push to the surface, and the melting rule is automatically implemented. So now we fix the action. So how do you get the algebra itself? So that's very easy. So this is just action of one generator. So now you just apply 2 generators, and then you change its order, and then you compare the 2, and then from that you can deduce all these quadratic relations. So you see, it's actually very simple. It's half a page for any paper. So once you have this, you might want to compare to other algebras who want to just see it in some other form. So that's sometimes necessary to convert this in terms of modes. So the mode expansion you can also read out from the algebras action on the crystal, and then you plug that in, you expand, and this is the I omit the 3 relations. So this looks more complicated, but you use this to compare to other things. So you see that for this special class of toy club Yao, it reduced to the alpha yang gel m/n, and for the generic ones, our algebra seem to be new. So I explained how do you bootstrap the algebra from its action on the crystal. So later it's confirmed by a direct equivalent localization of from the quantum mechanics by Galatov and Masahiro Yamazaki. Okay, so now I have to hurry. So now we have the algebra. So what do we do? Yes, so we want to consider all its representations. So far, what the crystal I mentioned is actually we call them canonical crystal. So they correspond to the, so in this BPS counting correspond to non-commutative DT chamber and without the open BPS states. So without the D2 on the disk. So for example, this is the canonical crystal for C3, and this is a canonical crystal for the resolved conifold. So it always start from one particular node here. So in this quiver language, that means this quiver is canonically framed. So in terms of this vacuum chart function, so is that the vacuum only contribute, the ground state of the vacuum module only contribute this factor. So it has one pole for whatever the nodes that your frame. So this is just what I said already. So now we want to, so we already know that in this BPS counting, we have crystal of other shape. For example, when you go to other chamber, so the crystal will look slightly different. And when you include when you consider open BPS states, for example, for this plane partition, you have a different asymptotics, which is labeled by Young diagrams. So we know that we already, there are other subcrystals. So it turns out we can actually consider arbitrary subcrystals of the canonical crystal.
Another quick question. Exactly what do you mean by an open BPS?
So earlier I said I have a D64, D2, D0 wrapping on holomorphic cycles. So here I can also have D2 wrapping on a disk that ends on the D4.
Okay, so these end on brain.
Yeah,
Thank you.
Yeah. So there's three questions. How do you describe an arbitrary subcrystal in this framework? And what's the relation of this to the quiver Yangian cell? And also, what do you have to do to the quiver? So the quick answer is that for an arbitrary subcrystal, you can write it as a superposition of positive and negative canonical crystals, and they will correspond to the non-vacuum representation of the quiver Yangian. And the only change is that you're going to shift the mode expansion a little bit, and it corresponds to a different framing of the original quiver. So let's see, if I give you a subcrystal, how do you describe it in terms of the canonical crystal? So I start from the near the corner. First, I determine the position of the positive crystal. For example, this is my subcrystal like this. So I see that it has these two blue positive crystals, and then but then when you go deeper into crystal, these two positive crystals will overlap. So to avoid overcounting, I need to add some negative crystal to cancel the overlap here. So I determine the position of these negative crystals. And then this negative crystal will also, so take this more complicated example. It has 3 positive crystals and then 3 negative crystals. But then the 3 negative crystals will also overlap later. So we need to add some positive crystal to cancel the overlap of negative crystal. So this, you just go on until it terminates. So now also there, you can have a subcrystal like this, where you just add by hand some negative crystal to have this shape. So in the end, so any simply connected subcrystal you can describe this way as a superposition of negative and positive crystals. So this example of this is a chamber for the conifold. So it has so this is instead of the pyramid, maybe it's also still called pyramid, but it has this ridge here. So this lens characterizes which chamber you are in. So now you have 3 positive crystals and 2 negative crystals here. So so to translate this into the representations, so remember for this for the canonical crystal, the vacuum contribute just this vector. So the first step you can only add your first atom. So now for this subcrystal, for the first step you can add all these positive crystals. So for each positive crystal, you have a pole for this Guangxi chart function, and each negative crystal will contribute a 0, and the position is the equivalent weight of this starting atom. So this will give you a very general representation of your original algebra. And so the only change to the algebra is this shift here. So I mean, so this is called a shifted Quiver-Yangian. So now you have a family of the for each Tor Yang. Now you have a family of Quiver-Yangian, but with it's like shifted the mode expansion. But essentially they are the same algebra, I think. So so the for the quiver, the translation is that if you start from the subcrystal representation, to translate to the frame quiver is that for each positive crystal, you add an arrow from the framing node to the to whatever color that this positive crystal is, and then a node from the back to the framing node for the negative crystal. And then you have to add some terms in your superpotential to complete this. Right, so we can put, I mean, it's essentially the same computation. We can bootstrap the algebra from the action, and then we can check from the quiver quantum mechanics for the frame quiver now. So now finally, we can also generalize the entire story to the trigonometric and elliptic version. So for this bound factor, and before we just have some, it's just this u plus h and u minus h. Now we replace this, so this will correspond to the rational case. So we replace this by a sinh, that will be the trigonometric or a theta function, essentially fixed theta function for the elliptic case. And so it turned out that it's possible to have a central extension. So the crystal now is the representation before the central extension. And then we can turn on the central extension by, and then fix the algebra by some consistency condition. So the base theory would be, for the trick is the 2D theory, and for the elliptic case is the 3D theory on curve. So, okay, so now I summarize. So, we consider a type 2A on a generic Toriclavial Cephal, and we look at the BPS sectors. From the BPS states is described by the set of colored crystals, and from this the action of this algebra, we can bootstrap the algebra itself. And in the end, we see that the algebra is actually very simple. Once I write down this quiver quantum mechanics, this quiver and superpotential pair, I can immediately write down this quiver-Yangian. And so you see that all the information is in this bounding factor here, and also a factor that characterizes the staticity of this E and F generators. So it's very simple. It's completely explicit, and it works for all Toriclavial in the same way. And and then we can consider the generic representations. So this is characterized by a subcrystal, and from this decomposition, you can write down the contribution charge function from the ground state, which determine the entire representation. And from the representation, you can bootstrap the shifted Yangian, and then you can confirm that this is indeed correct from the quantum mechanics of the framed quiver. And so this covers not just all the cyclic chambers, and also you can just have a very funny crystal of very funny shape, and this hasn't been studied before. And we can generalize to trigonometric and elliptic version. So for the potentially interesting future directions, so actually before we did this, there's some other way of trying to obtain this BPS algebra is by the instead of using this colored crystal basis, you focus on the pico web. You see that for each vertex, that will give you an alpha and G1 factor, and basically your algebra have all this alpha Young GL1 as subalgebras. And for each internal leg, you have some bimodule that connect these two vertices. So I mean, we tried with Pietro-Longhi for the simplest case. So it'd be interesting to see whether you can generalize this and compare to what we just got. Some of them might have a double algebra description. Maybe you can like see which one does. The simplest one does. I mean, this RPN GL1 GL n/m that has a W algebra description. And then finally, it's actually interesting to consider the truncation of algebra. So it's possible to produce a new rational UA and then the Q deformed version. And this truncation actually is the truncated algebra is more closely related to the system that other group has studied. And also maybe the meaning of this new subcrystal that we haven't seen before, and how far you can generalize this story to the fourfold. Yeah, thanks.
Thank you very much. We have time for some questions. Yes. Right.
So you mentioned the subcrystals. There is the idea that the F generators at the out of the subcrystal, right? You have to tune your parameters in such a way that the subrepresentation, but you just
No, it's not a subrepresentation. I mean, it's completely controlled by this the vacuum ground state chart function. It's as automatic as before. It's the same amount of parameter. The algebra has exactly the same amount of parameter.
But can this happen that you find atoms that you can't remove? I mean, naively you said you can always go back to the original successively removing the atoms. But could it be that for some specific choice of the H parameters, there is some atom that you can't remove because
but I mean, we don't want to, unless you want to truncate, we don't want to tune the H parameter. I mean, the two H parameter, we want to keep it as generic as possible.
True, but generic case that won't happen. But I'm asking, are there situations where it would happen for special values of the H?
I think that can happen in general. So in the original case, we started with the Subcrystal. So in that case, the only thing happens that the trunk is from there. But now we have a more general representation associated with Subcrystal. So it might happen that that it is not to cover, but somewhere at a point. It's like effectively truncating the Subcrystal, as you say, for very specialized parameters. And yeah, and then that should also correspond to truncation stuff. Yeah, yeah, I think that happens, and I think it's interesting to study that systematically.
Yeah, but this I mean, the truncation when you tune the H, it's a different type of truncation when you add this negative crystal by hand, right? I mean, here I can have I can just add a negative crystal here, but I still have the full general H parameters. I mean, this I mean, so I mean, in principle, this is a totally different story by the truncation via the tuning of the H parameter. I think Matthias' question is, suppose I start with this one, I mean, and then I change my H parameter. Could it happen that when you apply the F parameter, whether you can't go back? Okay, so I mean, so just take the frame partition, for example. I can imagine that you tune it such that it's so it's like you have a ceiling for you impose a ceiling, right? Say you truncate to W4, and then you can't go out, you can't go higher than 4. But then I mean already I can't have the, I mean if you want to have a subcrystal that's already go higher than your ceiling, then it's just not allowed. But as long as it's allowed, as long as it's below the ceiling, I don't see why you can't fix it back.
Okay, so if there aren't any, then